Alright folks, here's the answer key live while you watch. I'll go quickly, so it's only a couple of batches, I hope. Alright, doing the proof, we've got a triangle ABC. AB is equal, or really should be congruent to CB, so we're going to mark that. And point M here on AC such that it's an angle bisector. The only thing I can do is make this. Alright, you can't make any other assumptions yet about that. We're trying to do a proof that the triangles are congruent. Okay, fairly straightforward. First statement is, I'm just going to repeat what's up above, and you can maybe write it out again on a test, but that's the given. I'm trying to save time here. Step number 2 is we're going to say that AM right here, we're going to say that, let's see, MB and BM are the same. Alright, so I've got the givens, then I've got BM is congruent to MB, and that's the reflexive property. Okay, and I've also got then that, I'll call that angle 1 and angle 2 just to be fast. Angle 1 is congruent to angle 2. You can use 3 letters if you like that. The reason is that if we know it's an angle bisector, that is what the definition of an angle bisector is, that it breaks an angle into 2 equal parts. Def of angle BS. I love that. Alright, here we go. 4 then, we know that we've already said in the givens that AB and BC are equal. That's right there in the givens. And so I can say that the triangles right here, that's what I'm trying to prove, that the triangle ABM is congruent to triangle CBM, and that's because of side, angle, side. They're matching, that angle is included, so side, angle, side. So that's one proof. Step 5, I can just continue. It says you may continue one proof into the next. I'm trying to show that AM right here is equal to MC. So how do I know that these are the same? Well, I can just jump right there. That's AM is congruent to MC. Because of, you got it, CP, CT, C, that's the Henry Ford rule. That's that corresponding parts, these parts match up of previously proven triangles, proven congruent triangles, therefore they must be congruent. Alright, so that's another step, and then it says prove that AC is perpendicular. I'm trying to prove that is perpendicular right there. Okay, this would be maybe extra credit. But what you would do is you'd start saying, well, there's angle 3 and angle 4. So your step would be angle 3 is congruent to angle 4. That's also CP, CT, C. If these angles are equal to each other, okay, and then they add up to 180, they got to be 90. So I'm going to go along that route. I'm going to say angle 3 plus angle 4 equals a straight line. And that's really that the whole line is equal to the parts. That's whole and parts. And these are in the book on that page 668 or whatever. Whole and parts postulate. And then if I know that angle 3 plus angle 4 make the straight line, I know in step 8 that angle 3 plus angle 4 equals 180 degrees. That's because a straight line equals 180 degrees. That's a postulate also. That's just, we just say lines are 180 degrees. Then step 9 is, if 3 is equal to 4, I make a substitution. Angle 3 plus subbing in place of angle 4 what it's equal to, angle 3 equals 180. That's a substitution step. And then step 10, that 2 angle 3's equal 180. That's just combining like terms or doing the math. That's addition. And then step 11 would be angle 3 equals 90 degrees, and that's the division property of equality. Div prop of equality. And then finally step 12 is that AM is perpendicular to BM, and that would be definition of perpendicular, that they make a 90-degree angle. So def of perpendicular. You want your final step to read exactly as what you're trying to prove. Don't just stop when you're almost done there. Okay? So that's what that looks like. Moving on to the next page, looking at, it says give your expert analysis of the following definition, okay, and then write your own definition. A hexagon is a geometric thing with 6 vertices, all right? Well, a geometric thing is not very precise. What type of a geometric thing? We want to say that it's a polygon. And if we say with 6 vertices, well, something that has 7 vertices has 6 vertices. Something that has 8 vertices has 6 vertices. It's just got 2 extra, but it still has 6. So I would think that, I'm not going to take the time to write this all out, but I would say something along the lines of, this language is vague, and this language is not using the term that would be restricting 6 or more. So I want to say, in my definition, a hexagon is a polygon. Often you want to start it putting into a larger group of things. Polygon that has exactly 6 sides. Okay, vertices is really the wrong way to go because we don't define things by their vertices. We always talk about the sides, all right? So that would be my improved definition, all right? And you would write a little bit more detail about that. If each defect angle of a regular polyhedron, that's a 3-dimensional thing. Don't misread that. This is a polygon, but this is a polyhedron. I've had people misread that. If the defect angle measures 90, then how many vertices does it have? Well, the total defect angle in any polyhedron sum up to 720 degrees. So if I divide that by 90, I'm going to get 8. So it will have 8 vertices. Okay? It's got to have 8 vertices. In the next one, the perimeter. Find the perimeter with this inscribed circle. Okay? Well, I'm just going to use the properties that we went over in class. If these are externally tangent, then these have to be the same, so that has to be 9. These are externally tangent, so these have to be the same, so that's 16. Okay? So again, right here, just applying this concept over and over again, I need to find this by doing a little bit of subtraction, so that's 8, and that's 8. And I'm going to add this all up. So I've got 16 plus 18 plus 32 plus 22. All right? So 16 plus 18 plus 32 plus 22. Well, these guys make 50, and these guys make what? 38. So 88 would be their total then. All right? It says find the area of the quadrilateral if the radius happens to be 10. We've got that formula that says that the area of this thing is going to be the semi-perimeter times the radius. So the semi-perimeter then, S, is just half of this. So I divide that by 2, I get 44. So let's do it over here maybe. Area is equal to 1/2 the perimeter times the radius, which equals 44 times 10, which equals 440 square units. So whatever that would be. Okay. If you couldn't figure that out, just go with the 60 and put the 60 in place of the 88 and you get 30 or 300 units. All right. Find the measures of the following angles. All right. Again, if you see any angle whose vertex is on the circle, you take this angle, you go out to here, and you extend that, and you say it's going to be double whatever this measurement is right here. Well, that's 90, so this is 180. If we're told that this is 50 and all the way around is 180, the remaining bit here is 130, and so is that. So they're both 130. Be prepared to go in both directions. If there was some angle where you know the arc, you can take half of it to find the angle, which is what we have to do down here basically. If you're not sure how to do it, draw a line like this and say, what's this angle right here? It's going to be half of 66. That's going to be 33. There's this arc here that's 74. Half of that is going to be 37. And this angle right here then if we work on the triangle and subtract from 180, well, that's going to be the sum of these two, so it's actually going to be 70 degrees. So x is 70 degrees, and then if this is 150 over here, and these are both 140, 150 plus 140 is equal to 290, so this is going to be also 70 degrees. Alright, so that would be to make a total of 360. Probably should have chosen angles that didn't repeat like that, because that can be confusing, but that's just the way that one worked out.